I'm gonna present this paper, Uncovering and Mitigating Algorithmic Bias Through Learned Latent Structure. This is my first time presenting some paper, so it's not very good. Sorry for it. This paper is proposed by Alexander Amini in 2019. It is about alleviating the algorithmic bias in the machine learning systems, like bias to the race of the people or like gender of the people. Contributions from this paper are like they produced novel tunable debiasing algorithm, which utilize latent variables, adjust the respective probability of individual data points while training. So this is algorithm adjusts the probabilities of the data samples to be used for the training. For example, the traditional training uses all the data samples uniformly. This algorithm adjusts this probability to overcome the bias in the data set, and it has algorithm to find the bias in the data set automatically. We don't have to label the data set by with biases of the data set, like this is black people, this is white people, this is female, this is male. It automatically recognizes it, and the analysis and some experiments with this algorithm. So this algorithm based on variational autoencoders, which variational autoencoders are the models which fall under the generative models. They have encoder-decoder structure. Actually, there's autoencoder neural network. They are latent variable neural networks, so they produce latent variable of the input and produce the input again using the latent variable. This is trained fully unsupervised, trained self-supervised to reconstruct the input image. So hopefully the latent variable learns something like underlying probability of the data set. Variational autoencoders are on top of them. We don't directly produce the latent variables. Instead, we encoder predicts the probability distribution of the latent variable. Then we sample from that probability distribution, then decode to reconstruct the input image. So sample latent probability distribution is a Gaussian distribution. So we predict mean vector and standard deviation vector. And this is their algorithm to bias the training data set. So this part is similar to variational autoencoder, but we add another encoder. Encoder don't just output latent space closer variational autoencoder, but also outputs the activations for the output. For example, for the classification, the encoder outputs 2K plus D activations, 2K for latent space, and D for our supervised task, and latent space trained using reconstruction. So using latent, after predicting the latent variables, we can update the probabilities of training dataset based on the latent space, and this D activations can be used to train the supervised task. And here we block the gradients when y is 0. When y is 0 means like negative cases. we're only interested in the biasing of the positive cases. This is whole loss function for this neural network. So first, this is a classification loss, cross entropy loss for our supervised task. This is reconstruction loss for variational autoencoder. L1 norm of the predicted prediction and the input were input, and this is latent loss. We want our latent probability distribution to be as near as uniform Gaussian distribution. So we use Kullback-Leibler divergence to make it close to the unit Gaussian distribution. After learning the latent distribution, we can see which kind of data is more in our data set and which kind of data is not many. After analyzing that probability distribution of our data, we can adjust the probability of the sampling of our data, so we can more uniformly sample data to the model in the latent space. This is a algorithm they provided. So in every epoch, first we go through the whole training data and sample the latent variable, and this Q means the probability of the latent variable. So we update the probability distribution of the latent variables. QI. So for example, we have k latent variables, and we update for every latent variable. We update the probability distribution of the every data sample, and this W is the probability distribution of the sampling of data samples from the data set to the training algorithm. As you can see, it is inversely proportional to the probability distribution of the data set. So if some data is abundant, some kind of data with this that share the same latent space is abundant, it will be sampled less during training. Here we have alpha with hyperparameter to adjust the level of the biasing. If alpha is 0, subsample training set will tend towards uniform or latent variable z. If alpha is 0, it will be like there is no bias. There won't be no bias in the training data. If alpha is bigger than this probability, so if alpha is bigger than this probability, then this will be almost uniform, because this probability doesn't affect the probability of sampling. These 3 steps. After these 3 steps, we have probability distribution of the data set to sample for the real training. This traditional training algorithm, we just sample a batch from this data set, but with some another distribution, not uniformly, with our calculated probability distribution. Then we calculate loss function and update weights. This is sampling probabilities over the training data set. We can see here. This is like the discriminated quantified picture. This kind of picture, this kind of faces. Oh, I think I have this. I think Okay. Dataset is this PB. They use PBB dataset. Dataset is like faces and non-face, consists of faces and non-face pictures, and the classifier should predict if there is face in the picture or not. This dataset is originally provided to solve the algorithmic bias in the model. So in above picture, we can see the probability of resampling W calculated for the training dataset. So here B and C pictures, we can see the top and lowest probability top lowest resampling probability and top 10 highest resampling probability. Lowest resampling probability means these are abundant. This kind of picture is abundant in our data, and this kind of data is more or less. So this will be resampled more after learning latent variable and updating the probability distribution. Yeah, this data set is built to overcome the racial and gender bias, because this set doesn't contain like evenly all genders or evenly all races. So this is results, and this is a part is the results of the variational autoencoder. We hope that our variational autoencoder learns, like every latent variable learns something meaningful. For example, one latent variable can learn skin color, one can learn gender, one hair, or the position of the face. So you can see this variational autoencoder learns underlying latent space of the dataset. Then these are results from the debiasing algorithm. If there is not debiasing, we can see dark male. For dark males, accuracy is very low and variance is big. And light male and light female, there is not much. There are quite good in terms of accuracy, even without debiasing. But after introducing some debiasing, as alpha goes to 0, debiasing effect increases. So with strong debiasing, we can increase the accuracy for the dark male and dark female, but there will be a little loss in the light male and light female classes. But if we like average overall, it is increasing the whole whole accuracy of our model, and also the decreasing the bias. Here, the results are written in numbers. For example, with no debiasing, accuracy, mean of accuracy is 95%, but variance is 28, which is very big because of the bias in the algorithmic bias in the model. It performs very low for like dark males, so have very big bias. But including some debiasing factors, we can achieve both more accuracy and less variance. Less variance means we have less bias towards gender and race, and more accuracy means we generally increase the capacity, the performance of model. So this debiasing algorithm doesn't just remove the bias in the model, but also kind of improve the model in terms of performance. This is was yeah, this was like simple use case of this variational autoencoders for the biasing with simple case like classification. I think this can be like applied. This kind of can be applied to some uh, more more tasks like object localization, object detection, or maybe object segmentation. Uh, yeah, that's it.